Sure.
Okay.
All right, guys, thanks for coming. Very happy to have Nick here. I've known Nick for maybe 10 years, I think.
That's about right.
Probably, yeah. He's the co-founder of Cell Matrix. He recently also got a PhD from Virginia Tech. And he's going to talk about music, Nirvana, and Moore's Law. Very exciting times in itself, so we're all very curious to hear what you have to say.
All right.
Thanks so much, Nick.
Thank you. All right, well, I'm actually going to talk about these in reverse order from what I wrote up there. So let me start by saying that a lot of my work is motivated in part by the possibility that somewhere in the next 10 to 15 years, our world might experience a singularity. So a technological breakthrough that's so profound that most of the graphs you could make that chart human progress hit a discontinuity. So for example, Moore's Law, it's our favorite graph, of course. The nice steady doubling of transistor density every 1.5 to 2 years. It's been going on for decades, and some people worry that down the road this might flatten out, but it's possible that somewhere in the next maybe 10 to 15 years, this graph could skyrocket. And today we kind of wring our hands, yeah.
You want questions now or at the end?
Sure.
But isn't it reality that it actually flattens out?
Well, it depends how you count.
How real is the future?
But I'm not worried about it flattening out. I'm thinking that's actually going to suddenly jump up, and that's where the discontinuity is going to come from. This graph is going to skyrocket. And today you kind of worry about what do we do with 1 billion transistors or maybe 2 billion transistors. Tomorrow we might be asking a very different question. We might jump up to this 10 billion mark suddenly, or we might go beyond it. We might actually go up an order of magnitude and suddenly be looking at 100 billion transistors. Or maybe we could even go so crazy that we suddenly find ourselves in a situation where on one device we can put 1 trillion transistors. So what could this world look like post-singularity? How crazy can we get here? And I like to sort of go back to the natural world as a model of things. So if you go back to chemistry, you remember Avogadro's number, 6 times 10 to the 24th, number of atoms in a mole of carbon. A mole of carbon is 12 grams. And a mole of any element contains 6 times 10 to the 24th atoms of that element. And that's a pretty good number to work with. So let's talk about a mole of transistors or a mole of cores, CPUs, or some kind of computing element. I'll round down just to keep things simple. We'll talk about only 1 trillion of these things. And my basic research area is what do you do with 1 trillion computing elements? How do you architect these elements? What should they look like? How do they communicate with each other? How are they connected? How do you communicate with them? And how do you deal with some of the realities like imperfections when you manufacture the system, errors while it's operating, and so on? And what I've been basically working on is the design and use of a particular architecture that addresses some of these issues, and that architecture is called the cell matrix. And so I want to spend about 60% of this talk discussing the cell matrix, giving you a basic idea of what it is and how it addresses some of these issues. And then the second part of the talk, I'm going to kind of look beyond the immediate future into the deeper future and see what might come after this. A quick sanity check. Even if you get very aggressive in your transistor fabrication and you get transistors down to 1 nanometer on a side, if you want to build a device with 10 to the 24th of these, it's going to take about a square kilometer. And so you get the chip that ate downtown Portland. Not a really good form factor for your cell phone. But if you take those same transistors, but you can stack them into a third dimension, so your transistors occupy a cubic nanometer, that fits in about 1 liter, which is a much more reasonable form factor. So feasibility-wise, it's possible you could get here, and this leap from 2D to 3D fabrication is an example of the kind of singularity that I'm thinking about. Okay, 10 to the 24th transistors, what kind of engineering are you going to do on them? How are you going to use these? You're probably not going to do custom ASIC. Okay, once or twice might be fine. Custom ASIC, though, huge upfront non-recurring charges in terms of time and dollars, very difficult to validate, and at the end of the day, you've got a single function device. A better approach would be something like an FPGA. Everybody here comfortable with FPGAs? Okay. Programmable logic, fixed hardware. You do your ASIC once to build this device, and then you load memory values into it, and that changes how the system behaves. So you can basically implement your custom circuit on top of this meta layer.
Okay.
And Xilinx and Altera, for a number of years, have made good arguments as to why this is a good way to use a large transistor budget. Much lower non-recurring costs, faster time to market. You can spin a design in a few hours instead of months, and more flexibility in the field. And these arguments simply become more compelling as you scale up from where we are today, 15 orders of magnitude, to say 1 trillion transistors. And so this is my first of 4 hypotheses about future directions in computing. that sort of drive the whole cell matrix idea. This first hypothesis, it's more of an observation. As you scale up, it makes more and more sense to be building reconfigurable hardware instead of fixed function. Now today in FPGA, basically you run software on a workstation like a PC. You take a design for a circuit, you compile it, and then you run it through these wires and you feed it into the reconfigurable device, and now your device turns into your target circuit. That's today's model, and you basically configure it and then you use it. Tomorrow you might do something different, because when you scale up your number of transistors, you scale up the number of reconfigurable elements you have. Today, 100,000 elements is a big device. Tomorrow you might have 1 trillion elements. And so one thing you can do is you can start implementing millions of distinct circuits on this single device. It could be like a shared resource with lots of different circuits operating independently, kind of the same way that a CPU runs hundreds or thousands of different processes on it. And you can start imagining very dynamic behavior to these circuits. You might have registers that grow and shrink based on the scope of the input data. You might have on-the-fly reconfiguration where you have an arithmetic unit and it suddenly gets reconfigured into a string processing unit as the input data changes. Or you might have a circuit here that's doing numeric processing and have a watchdog circuit looking at the I/O, doing statistics on it, and comparing it to expected distributions. And at some point, this watchdog may say, there's something strange going on in the inputs and outputs here, maybe there's a problem. It could pick up that circuit, temporarily move it somewhere else in the array, and then start testing the elements that it was built with to see if there's a defect in the hardware. So you can start imagining all these sophisticated behaviors taking place, millions of points throughout the reconfigurable array, all simultaneously. And you can't really do that if you're driving everything from a PC and running it through a few wires. That's a show-stopping bottleneck. So hypothesis 2 is simply the idea that you may want to take that control and management and move it inside the device. So you have a system something like this. You have a base layer of reconfigurable elements, and you have a control and management system sitting on top of it. And this is a very sophisticated piece of circuitry. And some of the things you might want to do are on that last slide, but you can probably think of other things that you'd like to endow this layer with. And how do you design that? What should its architecture be? And you can put that into custom ASIC, or you can go back to hypothesis 1 and say, maybe this control and management system should also be reconfigurable, just for more flexibility. So that's the third hypothesis. The CMS itself should also be reconfigurable. And now your picture looks like this: base layer of reconfigurable elements, control layer, which is also reconfigurable. Well, how do you control CMS1? Well, you put another circuit on top of it. And you can make this fixed hardware, or for flexibility, you can leave CMS2 flexible. And now you put a layer on top of that, CMS3. And now you're left with what controls CMS3. So how far do you want to stack this hierarchy? Now, in practice, this may be plenty of flexibility. You may be perfectly fine building some sort of custom circuit on top here to do this configuration. But in theory, there's something interesting going on. Basically, all of this is the software of the system now. This is all the stuff that can change after you've done your manufacture. And the stuff above this line here, that's the hardware. And so this question is really one of, where do you want to put that line? Where do you say, that's enough software, this is where the hardware begins? And hypothesis 4 says, maybe you don't. Maybe what you can do is somehow close the loop, put this top layer under the control of the base layer. And now you've basically eliminated the hierarchy, because there's no layer here that's the controller of all the other layers. Everyone is a controller and also being controlled by another layer. And that's hypothesis 4. Simply that it may be interesting if you can collapse this hierarchy, remove the distinction between controlling and controlled objects. Now, this is the hypothesis that really drives the interesting aspects of the architecture. So I'm going to spend a fair amount of time talking about this. This also includes the other 3 hypotheses, sort of by default. Before I go into the engineering aspects of this, I want to talk about the motivation. I want to talk about where it comes from, because that'll help in sort of understanding the mindset of why you want to do things in this way. And the origin of hypothesis 4 comes from something called non-dualism, or dualism. Subject-object dualism is a way of looking at the world in which you see subjects and objects as being independent of each other, as having independent, distinct roles from one another. So as a very simple example, look at a sentence, I kicked the ball. There's a subject, I, and there's an object, the ball. And kick is the action, the verb. And I, as a subject, am performing an action on the ball. There's a directionality to that. I'm the one who's doing something, the ball is being done to. And in this dualistic way of looking, these roles are very distinct from one another. And this changes how your language is structured, how your science is built, how you interact with the universe in general. And it's sort of a Western mindset. But nonetheless, after many millennia, Western science made a remarkable discovery that when I kick the ball also kicks me. When I apply a force with my foot to the ball, it applies an equal and opposite force back onto my foot. And so subject-object is not so clear a distinction, because at the same time I'm kicking the ball is a subject acting on me as an object. And that's our first hint of a non-dualism, the idea that there's an interdependence or some sort of interrelationship between subject and object other than this directional nature. Okay, I'm going to give you a slightly less philosophical example of this. And this example is the one that started all of this research back in 1986. And it's a very basic computer science question. How do you write a program that prints out its own source code? And theoretically, it's very easy to do. 3 steps. First, you create an array of strings. And then you write a program that reads that array and prints out each string. And then you take the code of that program and you use it to seed the array. And you take that, compile it up, you run it, and it should print out source code. So we can do that. Here's our initial array. It's a character array with 100 placeholders for it. I think it's going to turn white in a second. Yep. Here's the main program. It reads the array, prints out each line with a new line at the end. We're almost done. All we've got to do is take this code now and put it into the array. So the first entry in this should be this static character declaration. We put it in quotes because it's a string. And the second entry should be this quoted string that we just created. So we can put that into the array, and we put backslashes to escape the quotes. And the third entry should be this string, and we put backslashes in front of the backslashes. And we make the fourth entry. We're doing really good, right? We've got 4 lines written already. Well, what's going wrong here? We're doing stuff, but we're not getting any closer to a solution. And the problem with this approach is you're looking at the code and data dualistically. You're seeing the subject and object as being different from each other. The program is the subject, and it reads the array, which is the object. And we think that's all that's going on. We're treating these things as distinct. And as long as you do that, you cannot solve this problem, because in fact, the code and data are related. Anytime you change the code, you need to change the array, because it's supposed to be a copy of the program. But when you change the array, that's part of the program, so you're actually changing the code at the same time. So until you discover this interrelationship, you're kind of doomed. You're not going to be able to solve this problem. But you can solve it. Okay, so it fits on 2 pages here. This is the first line of the program. It's the array declaration, 20 lines. And this is the main program. And it looks very similar to what we tried before. It basically reads the array and prints it out. But if you compile this and run it, you get exactly what I just showed you on these 2 slides. And the reason this works, and what we did before it doesn't work, has to do with the fact that we've basically taken part of the data and we've moved it into the code. For example, the fact that you need to escape certain characters with a backslash, instead of storing that in the array itself, we've embedded that information in the code. Somehow, it seems like what we've done is we've sort of admitted that there's this relationship between the 2 pieces, and by doing that, we've sort of broken this hierarchy that we had in the previous attempt to solve this, and that gets you to an actual solution. And an interesting way to think about this is, what is this thing that I showed you on the last 2 slides, this collection of white marks on a blue background? Is it code or is it data? And it's code because it's a program, it's got good syntax, you can compile and run it. But it's also data because it's the output of a program. It's actually the output of this program. So is this code or is it data? It's actually something different. It's some higher level composite that simultaneously is both. And so this completely eliminates the distinction between code and data. And from there, you can get to the actual definition of a cell matrix. And the cell matrix is basically a hardware embodiment of this concept. So a little bit of engineering. This is a 4-sided cell matrix cell. Each side, I edited this slide at the last minute. I know I shouldn't have done that because a lot of my labels have changed from white to black for some reason. Open office weirdness. This is a 4-sided cell, part of a 2-dimensional matrix. 2 inputs and 2 outputs on each side, labeled C and D, compass directions for the 4 sides. We're going to ignore the C inputs for a moment and think of this as a 4-input, 8-output device. So 4 data inputs and then 4D and 4C outputs. And the way you specify how it maps inputs to outputs is just with a truth table. So you have each combination of 4 inputs, 16 rows, and for each of those you have 8 outputs specified. And that 128-bit pattern, that's the signature of the cell. That's the configuration memory. And you load that into a cell, and it tells it how to map inputs to outputs. And then to build the entire matrix, you basically just take a collection of these cells, you tile them, connecting nearest neighbors to nearest neighbors, and this is your cell matrix. This is a small 4x4 example. The edge elements, you have access to the C and D inputs on the edges. The internal ones you don't have any access to. Okay, every element is accessible only to its 4 immediate neighbors or to the outside world if it's on an edge or a corner. And you basically configure the memories to perform simple logic functions, and by configuring cells in the right position you can create circuitry. So very simple circuit that does an exclusive OR. Does an OR of 2 inputs A and B. Now, a slightly more complex example, each of these little blocks is a single cell. Okay, so this is hundreds of cells in each direction. And this is an IEEE 754 compliant floating point unit. And you're looking at a simulated window of simulated cell matrix system. The white regions are cells whose truth tables are all 0. They're uninteresting. They're background. The dark green regions have interesting truth tables, but all the D outputs are 0. And the bright green regions have at least one D output asserted. If a C output was asserted, it would be red. Well, you won't see that in here. And what I've built in here is an addition unit and a multiplication unit and a feedback path, and this does repeated multiply adds to do polynomial evaluation. It reads the coefficients from down here, and I've seeded this with the coefficients from the Taylor expansion of e to the x. So this circuit will compute exponentials. You feed in a floating point number, and it loops through and evaluates the polynomial. And you can just kind of get an idea of sort of the basic data flow. Now the simulation is sequential, so it's slow. But in real hardware, of course, most of this would be happening in parallel and it would be fast. So we've got the initial seed coming through to the top, and then you'll see just a few iterations as it loops through and does these multiply add cycles and computes the value. In this case, I was computing e to the 0, an interesting number, but easy to check. And at this point, it's useful to point out that the architecture of the system is perfectly scalable. Okay, now there's going to be speed and clocking issues and things like that, but architecturally, if you want to make a bigger matrix, you can take 2 matrices and just connect them together on the edges, and you get a bigger matrix. You don't need to change anything in here or anything in here in order to join them together. So the architecture is scalable. All right, so the other piece of the puzzle is how do you configure an element? How do you set up its configuration memory? And this is what the C inputs are used for. If you set a C input to 1, then you can shift in a new truth table on that same size D input. And as you're shifting in truth table bits, the cell is shifting out its previous truth table bits. So you can read and write an element's truth table simply by accessing its C and D inputs on any of its sides. Which means that all of the edge cells can be configured from outside of the device by hitting the C and D lines. Very simple example. This is one cell which you load this truth table into. It puts a 1 out to its northern control output. It takes data in from the north, sends it back to the north, and also sends it down to the south. So when you configure this cell in this way, it basically reads the truth table from the cell above it. It restores the truth table, so it's a non-destructive read, and it sends those bits down to the south. This is the beginning of a dynamic circuit that's basically able to read circuitry somewhere else in the array, do some processing on it, and then possibly modify it. Now, a question is, how do you configure elements that are not located on the edge? So this element in here, if you want to load some target circuit into there, you have no access to its D and C inputs, but this element does. This can access its D and C inputs. And so you can use this element and actually the element below it to build a little circuit that will give you access to this internal cell. So this D input drives the target's D, and this D input is routed through into the target's C input. And now you have control over this internal location. And you can do an inductive argument on that to basically show you can configure any cell anywhere within the array, no matter how big it is. And this introduces the idea of sequences. A sequence is simply a collection of changing D and C values that perform some desired configuration operation. So here we had to configure this, and then we could configure this internal cell. And we just call that a sequence. And a supersequence is a sequence of sequences. And the quintessential example of a supersequence is bootstrapping. So suppose you have this region of 25 blocks, and each of these blocks might be more than one element. And you want to bootstrap it. You want to load some configuration into this lower right region, and you only have access to the upper left elements. Well, what you can do is you can use your access to the D and C inputs up here to configure this first region of cells to be what we call a wire. And a wire basically gives you control to the D and C inputs somewhere to the east. Okay, that's what I showed you in the previous slide. You can use that access to configure the second set of regions, set of cells, to be a wire, and then a third, and then you can configure this block to be a bent wire, and then you can configure this block to give you access to this target cell and load some desired configuration. Then you reconfigure this block to be a straight wire, and then you use it to access another off-axis cell. And you can do it a third time and a fourth time. And you'll notice this continual back and forth between subject and object. First we're configuring this block, and then we're using it to configure something. And then we're configuring it again, and then using that to configure something. And this back and forth between subject and object of configuration, this happens all the time on this architecture. And all you need to do this is just to perform the right sequence of sequences. So we did 3 extension to the east steps, a turn to the east to the south, and then 3 configurations off axis, followed by extensions to the south, and a final configuration. Now if you repeat this super sequence, but you start with only 2 extensions to the east, then you do exactly the same thing, but you configure 1 column further to the west. And you can do that a total of 4 times, and now you've configured this 4x4 region. So you can bootstrap the system. The burning question is why? Why do you want to do this? Why not just have row column addressability or make a scan path and drop your bits in as you snake through? Is there a practical reason for dealing with all this non-dualistic nonsense? And one of the reasons is yes. I mean, the answer is yes. One of the reasons is speed. So there's a particular circuit called the Medusa circuit, and the corresponding supersequences, Medusa supersequences, and they're useful for tiling a large region of your matrix with subcircuits that are very similar to each other. For example, if you wanted to do a finite element mesh, you basically have a repeating pattern of blocks sitting side by side, nearest neighbor communication. This is a really efficient way to bootstrap such a system. And it works something like this. Again, we've got a 5x5 region here, multiple cells in each region. And you only have access up here in the upper left, so you use that access to configure this upper left block to be a Medusa circuit. Now, one thing a Medusa circuit will let you do is pass information across it into a neighboring region. And you can use that access to basically build a second Medusa block. So it's sort of a bigger wire. And you can use those 2 blocks together to configure a third and a fourth and a fifth. Okay, we've done 5 time steps, and we've configured 5 blocks. In the next time step, you can set a flag, and each of these blocks will in parallel configure a region to itself. And now you've just built 5 more blocks in a single time step. And you can do the same thing. You can have those continue to the south. And now after 9 time steps, you build 25 regions. Okay, now on a 5x5, it's a modest speed up. If this was a trillion by a trillion, you get a much more significant speed up. And you can deal with defects in this. I'm not going to go into the details of it, but you can test regions before you configure them to see if there's defects. And if there are, you can avoid them, and then you can fill them in later on below. Question?
So would you get even better gains in 3 dimensions?
Mm-hmm. Absolutely. Okay, that's just the basic supersequence. Extend to the east until you make no more progress, and then extend to the south in parallel until you make no more progress. And so I can show you a picture of this. This is a simulator, a 3-dimensional version of a cell matrix. And you're going to be looking down on the z=0 plane. We're going to see exactly what you just described. And you can see this move over, turn, come down, and configure off-axis bootstrap sequence. So we're building 5 Medusa blocks across this first row. And after those are built, they'll operate in parallel and configure regions to the south. And again, the simulation slows down because it's a sequential machine it's running on. But each of these steps, each of these rows should build in the same amount of time as it takes to build 1 element. And now all 25 of these blocks in parallel configure a second sheet at the z=1 plane. And then if you continued this, once you built this sheet, those in parallel could configure another sheet above. And it's a very efficient way to do bootstrapping. It's basically order square root of n for a two-dimensional system. For a three-dimensional system, it's actually cube root of n. If you want to configure n elements or n regions, it takes you roughly cube root of n steps. And it's a general scheme. It's not just for configuration. You can do testing and analysis and defect isolation and other things like that in parallel and get the same kind of speed up. For an example of time, suppose you had 10 to the 24 blocks or elements that you wanted to build using this system, and you have a 1 terahertz clock. 10 to the 24th elements, 10 to the 12th per second on a regular FPGA, this is going to take 1 trillion seconds. Okay, 32,000 years to do the configuration. On a two-dimensional cell matrix, it's going to take you order 10 to the 12th steps with 1 terahertz clock that's on the order of 1 second. And on a three-dimensional one, it's only going to take you 10 to the 8th steps. That's 100 microseconds. Okay, fabulous speed up here from a purely sequential system. Even the two-dimensional one is significantly faster, and the 3D is minuscule. Basically, all you're doing with the cell matrix is you're sort of extending the design space. We're saying, let's not just build circuits that process data. Let's not just look at binary values and process those. Let's start processing hardware, circuitry. Let's, in some sense, start making the hardware version of self-modifying code. And it's a very useful feature to be able to do. Now, I gave you one example, which is parallel configuration, but there's other things that you can do with this self-modification. You can build circuits that are entirely self-replicating, that you load into the system, and as soon as you place the last cell, it starts making a copy of itself. And you can use that as a carrier to start with an initial seed and sort of embryologically populate your region with a collection of these seeds and then have them differentiate and interconnect and so on like that. You can do runtime scrubbing of circuits. You can look for errors in configuration memories, upsets, and correct those on the fly. You can use this as a process driver to debug a foundry process by building wafers with cell matrices on them and using the cell matrix circuitry to analyze different pieces of the substrate that you built. And you can actually, if you stack these wafers in 3D and you have alignment issues, you can actually detect and do some degree of correction of those using cell matrix circuitry. So there's a lot of applications that you can use this self-configurability for. A lot of interesting questions, and I'll give you website information at the end. There's some papers that talk about all these different ideas. Question?
So you mentioned about the configuration happening parallelly, 2-dimensional and 3-dimensional, but is it different configurations for each cell, or is it like just replicating it?
Well, in the simplest case, it's just replicating. But you can start doing things, for example, it's easy to build in positional information into a block. You have an adder that takes in a column number from the left, adds 1, sits it out to the right. And so now each column can know where it is, and you can start doing differentiation based on positional information, for example. So you could build some initial circuit that would be the same as every other circuit. Then they can self-modify into whatever particular pieces of a final circuit you're interested in. You can also do some of that while you're configuring it by putting the same mechanism into the Medusa block itself, so that it actually configures different circuits as it's moving.
Got it. So I was wondering, like, okay, if an external environment is like trying to configure, wants to configure the entire 25 cells you mentioned, and so is it like in your first step itself, you just load everything into the first cell, and then it parallelly then configures? Is it?
Yeah, that's one way to do it.
Okay.
And there's actually some papers on the website that talk about that from 2002.
But you mean everything, the whole configuration bit stream? I think that's your question.
Yeah, that's what I'm asking.
Well,
that's not the case.
It's not literally the bit stream, but you store something like a genome, a higher level functional description of what you want each block to be.
Okay.
And each block has a library inside it that it can use to decode that genome and say, I should be a flip-flop, I should be a gate, and so on and so forth. And yeah, that's definitely one way to do it. So that's generation 1 of the cell matrix, and it's been implemented in various forms. There's simulators, there's various development tools, there's multi-CPU simulators for doing faster execution of parallelism. There is a briefly commercially available version of this called the Mod88. Each of these boards implemented an 8x8 matrix, and the LED showed you what was going on inside the device. Underneath the board, there's a Xilinx Spartan FPGA, because custom ASIC is expensive. So we implemented it on top of a Spartan. And you could snap these boards together on the edges to sort of model the scalability of the architecture. And you could drive it all from a PC to a parallel port, load in initial configurations and so on. This was actually the first prototype. This was 2-micron CMOS, 1986. And we didn't quite get to a trillion cells. We had to settle for 12. But it was a good proof of concept. We actually were able to do some defect detection and some internal configuration and so on. So that's generation 1. The problem with that is the world isn't binary. We treat it as it is, we digitize things, we approximate things. The world, of course, is more analog. And so could you make an analog version of this? And yeah, you definitely can. And this might be generation 2. Each of your cells throw an op amp in, maybe a few other components, put in a network of resistors and capacitors, digitize those, make them digitally controllable. Your truth table now has these digitized values, and if you allow special values for resistance and capacitance of 0 or infinity, you can configure this into all the useful circuits that you're used to, amplifiers, inverters, differentiators, integrators, and so on. And you put in the C mode, a way to serialize these values and exchange them from cells, and you can come up with an analog version. And that's generation 2. And I have more details on that, but I don't want to talk about that. What I'm really interested in is generation 3. So what's the third version of this system? Well, this is sort of a trick question, so don't think about it too deeply. Desert island question. How do you turn a scanner into a scientific calculator? So you've got electricity, you've got a PC to run your scanner, you've got a scanner, but you don't have a scientific calculator, and that bothers you. Okay. The answer, so you need some magic flashcards, first of all, that show pictures of like sines and exponentials and things like that. You put the flashcard on the scanner, you send the commands to drive the scan mechanism to a position X units from the edge. You take a scan, and now you look at the array of elements you read, and you find the one that shows the reflection of a dot. And how far up the array that is, that's the value of sine of that value X. Okay, all you're doing is you're reading a graph, the way that you and I would read a graph. If this is 12 1/4 inches across and 2 inches high, and you want to know the sine of 7, you measure over 7 inches, you measure how far up until you get to a green dot, and that's the sine of 7. Okay, we all do this without thinking about it, but what if you could somehow capture this process inside a cell? What if you could actually store a function y equals f of x inside one of your cells?
Cells? You mean actual biological cells or cell matrix cells?
Cell matrix cells, which could be biological. Some kind of computing element. So for example, you might store a function y equals sine of x. And surprise, if you want to find the value of x, you put that into the input, and on the output you find the sine of x. Or you might have a multiplier that multiplies by a constant a, and you just have to store this line with a slope of a. If you can store these waveforms somehow inside one of these computing elements, you can compute the values of these functions simply by sampling that waveform at the right point. Okay, so how do you do this? Anybody know what this is?
Magnetic drum.
Close. It's actually a mercury delay line-based memory, at least according to the website, although I would trust your judgment. The idea of this was you had a tube filled with mercury, and you could put a waveform into it by applying pressure waves at one end, and that waveform would travel across the tube. And when it got to the other end, you could pick it up, sense it, amplify it, feed it back in to the beginning, and you could capture a waveform. And this was used in the UNIVAC system to store data. Okay, the reverbulator, this is a guitar effects box. You basically take your guitar input, you put it into the input side, and it runs a small speaker that drives the end of a spring. And the wave travels down the spring. It takes 1/4 of a second or ½ second to hit the other side. When it gets to the other side, you hit a transducer, turn it back into a voltage, and send it on the output. And you can also feed it back in and mix it back in with the original input. So it's an echo unit. You play a little riff, and it goes through there, and it starts playing back over and over and over again. It's a cool little effects box. And what you're doing is you're capturing a waveform coming out of your instrument, and you're storing it mechanically in this vibrating spring. And you're doing it in a way that you can preserve it inside this box. And so these are some ideas on how you might be able to store a function of one variable, a continuous valued function with certain requirements on continuity and differentiability. But you can store something like y equals f of x inside this mechanical system. Okay, now doing C-mode operations on this is pretty simple. Basically, you would have one element with a waveform in it. You want to be able to read that waveform and store it somewhere else. All you have to do is sample the output. And if you take that output and you put it to the input of another element's spring, it will replicate what's stored in this first element. Or you could load a new value into that first element by just feeding the input. So you can do something like a C-mode on here. That's not too hard. D-mode is a little more interesting. And in some sense, this is sort of what happens in music. Okay, music is basically just a series of vibrations. And when you sing a song and somebody else hears it and they start singing it, that's basically just a transfer of this vibrational pattern. Okay, it's kind of like a C-mode thing. Okay, D-mode is trickier. So here's this spring or this tube of mercury. You have your wave coming in on the left. It travels in this direction, and at the end it recirculates back. If you want to evaluate this function at some point x, well, the function itself is sort of moving throughout here, and let's just assume it takes 1 second to travel from one end to the other. If you want to know the value of the function at 0.25, you can basically build a sample circuit that sits here at the edge of the tube, make a marker tube that tells you where you are in this wave, and you just wait the right amount of time until the value that you want, the function value at, say, 0.25, hits the end of the tube, and then you read the sample, and now you know what the function is. Okay, that will let you evaluate the function, but there's this time penalty. It may take up to a second to read the desired value. Now you can cut down the time penalty by putting in 2 samplers, and now at the most you have to wait a half second. And depending on where your value is, you wait till it gets to one of these points, and then you read it out. Okay, if you have 8 samplers, you cut your time down to 1/8 of a second, and obviously the more of these sample points you have, the quicker you can get the value out. But at this point, you can do something else. You can say, I'm willing to wait 1/8 of a second, and you can wait till your value gets to the closest sampler and read it out. Or you can say, I don't want to wait. I need to know the value right now, but I can accept a bit of error. And so you can simply choose to sample at the point closest to x, and say, I might have an error up to 12.5%, but I can get the value out immediately. Or you can do something in between. You can say, I'm willing to wait up to a 1/16 of a second, and accept an error of 6.25%. And now you're sort of using both of these techniques, and you're going somewhere in between. And you're basically playing a trade-off between speed and accuracy. And somehow, this starts to seem a little bit Heisenbergish to me, where you've got these two things, and you can't insist that they're both perfect. You have to choose which one you want to be perfect, or how much error you're willing to accept in each. And so I'd like to come up with a relationship like this for this readout process. Okay, those are functions of one variable. What about 2 variable functions? Function of x1, x2. Well, one way you might store this is if you had some sort of deformable membrane. So a sheet of rubber or malleable plastic or something. And at each point, x1, x2, the height of that membrane tells you the function value. And C-mode in this case is somewhat tricky because to send this thing out from a D output, you need to somehow serialize it. So you can establish a scan pattern where you move across like a raster scan, and use that to pick out the values at certain discretized points. I'm wondering if there's a way to use a space-filling curve, some sort of limit of a sequence of curves that would let you basically sample every point on this region in a finite amount of time. Okay, this is the point of the talk where I get a lot of question marks on my slides. Another idea, have you ever used these pin art toys that you get at Spencer's? Series of pins hanging down, and you can put your hand underneath, and you get an impression of it on top. And that's an interesting way to store a function in 2 variables. The function value would just be the height of each pin at a point x1, x2. And C-mode on here is not so bad. If you had a way to sort of trap these pins in a certain position, you could take another pin art and just sort of push it down on top and make an impression of the first one, and there's your C-mode. You've taken this function of 2 variables, and you've replicated it somewhere else. D-mode is more complex because there you almost certainly need some kind of raster scan method, some way to be able to pull off the value of this function, the height of a pin or the height of the membrane at some point x1, x2. There may be a way to do this if you have a traveling wave similar to the spring in the 1D case. If you can have a flexible membrane and sort of have a waveform in 2 dimensions traveling across this, and have sensors on the end, and then again you can pick them off in a certain amount of time, or have multiple sensors and so on. So that's probably doable in some way. Function of 3 variable gets even more interesting. So how do you physically store f of x1, x2, x3? An intuitive example might be to use temperature. So x1, x2, x3 gives you a position in a room, and the temperature at that point tells you the value of the function. Okay, now temperature is not a good one because heat flows. It's very hard to preserve that. That's just the intuitive idea. A more practical example might be if you could use the phase of light at different points within a 3D region. Use the phase to encode the value of the function. And that begins to start to look like something like a hologram. And C and D mode here is fairly complex. I'm not going to go into ideas on how to do that. But once you have a function of 3 variables, that may be enough to make a 2-dimensional matrix. Okay, you use 3-sided cells and you tile them as alternating triangles. So that may work for a 2D matrix. If you really want to do a 2D matrix and possibly a 3D, you need a function of 4 variables. And the only idea I came up for that, again in this sort of intuitive example, is to use time as the 4th variable. So x1, x2, x3 would give you a point in the room, and then x4 tells you how long to wait until you sample. And it would have values between, say, 0 and 1. And if you can change this temperature over time, repeatedly, you can pick off the value at some point, x1 through x4, by looking at the temperature at the right point and the right time. And in the electromagnetic example, this might be changing the phase at different points in this region over time, which is almost something like a holographic movie. Okay, now the physics here is way beyond me, but that's one of my summer projects, is to try to come up to speed on some of this. And this generation of the system is probably not going to happen in 10 to 15 years, because these kinds of ideas are a very different direction from where computing is going today. It's going to be sort of a singularity after the coming singularity, perhaps, before you can actually build something like this. But some ideas there to think about.
I have a question here, because I'm getting a bit confused. I mean, in computer science, we are used to using abstraction, and it seems you are going exactly the opposite way.
Yeah.
You want an as direct representation as possible.
Absolutely. That's
a good remark.
Okay, thank you. A few quick examples of what you could do with this. So a simple function of 1 variable. You make a fixed gain amplifier. Right? You put in an input, you get out 10 times that input. And again, you just have to store this function y equals 10 times x.
Maybe a follow-up question, though. Is your intention going somehow closer to the physics, actually?
Yeah, going closer to sort of how the real world seems to.
The real motivation for that?
Yeah. Variable gain amplifier is just a multiplier. You put a gain in the top x2, you put in your information x1, and you get out x1 multiplied by that gain. And you can also do good old-fashioned multiplication with this. And you just have to store this function of 2 variables, z equals x times y. Sine wave generator, you could basically take a cell, store a sine wave in its truth table, and put the cell in C mode, take the output, send it back in, but also take a copy of it and send it out, and you get a sine wave coming out of this. And if you take that and you feed it into a multiplier, you get an AM encoder. You have a carrier wave here, and then you modulate it based on the information you send into the input. And it takes you 2 cells to build this. Sawtooth generator works just like a sine wave generator. You just store this different pair of ramp functions in the cell. And now you can make an FM encoder. You feed in an input, and you get out a sine wave whose frequency corresponds to the input value. And you can make a better AM encoder with 3 cells. Basically, you use a base frequency, feed it in here to get a sine wave at that frequency, and then you amplitude modulate it with a multiplier, and you get your output. So now you can tune it and pick your station. And all of these things, these are just using simple 2 input functions. Okay, if you actually went to cells where you had 3 or 4 inputs or more, you have a much wider scope of possible applications. And it's very different, as has been pointed out, it's very different from how you do like digital signal processing today, where you take an input, digitize it, do a Fourier transform, and follow this algorithmic set of steps to get some answer. To me, it's somehow more in tune with kind of what happens in the real world. And it kind of leads me to this question of, like, are we somehow just reinventing music in doing all of this? Now, there are Aboriginal cultures in Australia that have been around for 40 to 50,000 years. And some of these cultures have a creation story that speaks about the dream time. The dream time was the beginning when the world was flat and featureless. And these creators came down and they traveled around the land. And as they traveled, they sang songs. And when they sang about a cliff appeared. And when they sang about trees, trees appeared. And when they sang about a river appeared. And they basically sang the world into existence according to these stories. And these stories are obviously a very important part of this culture, so they're passed on from generation to generation. And how do you pass on a song? We already talked about this. You basically sing it. Somebody else hears it, and they internalize it. And then later on, they can replay it, and somebody else can internalize it. And when you sing it, you also hear it, and that sort of reinforces it in your own mind. That's sort of the non-destructive part of it. So this is a little bit like C mode to me. This passing on of these creation songs. Now, there's a thing called song lines. Song lines are these unmarked paths across the land. Some of them are short. Some of them would take several days to travel on foot. And the way people navigate these song lines is by singing the creation songs. You begin at one point, and you start walking, and you sing these songs. And the songs tell you which way to turn. They tell you there's water over here, there's shelter over here. And basically, by knowing where you are in a song, you know exactly where you are in the land. And so the information about the land is basically extracted from the playback of these songs. And that kind of sounds like D mode to me, because you're not just making a copy of this vibrational pattern, you're processing it somehow. You're saying, here's the pattern, sample it at a certain point, and then do something with that information. You're pulling that information out based on an analysis or a processing of those vibrational patterns. So the laboratory implementation of this third generation cell matrix is probably going to wait for the singularity after the singularity. But in some sense, there's aspects of this culture that have been an embodiment of these same principles for like 400 centuries. And I think that's pretty cool. That actually inspires me a little bit to think that maybe going down this path might lead somewhere interesting. So on that note, I'll just give you some contact information, and I'll say thank you for your attention, and I'll be happy to take any other questions.
What have you built for this third experiment?
What have I built?
Yes.
Nothing.
But do you have ideas?
Yeah. I think it would be interesting to start with functions in one variable and actually use something like a spring-based storage system and just build some of these blocks. I mean, they're going to be big and clunky, but just to sort of put some of these together and start doing some of the processing on them, do some of the sampling, come up with some more mathematics to describe the limits on sampling in terms of time and accuracy, and see what you can do with it. Get some papers out there, find someone with a physics background to say how can we go to a function of two variables, and go from there. So yeah, this is definitely an area that I'm interested to pursue.
Yeah.
Why not using MEMS or something?
Using what?
MEMS, micromechanical elements.
Like what?
Well, they can build springs at the microscale.
So you could build a little tiny pin art thing, for example.
Yeah.
Yeah.
Pretty small, I think. So.
Yeah. I mean, the advantage of the spring thing is I can do it in my garage.
Yeah.
And I can do it on my budget.
Right.
But yeah, definitely next step, mechanical systems at a small scale. There's definitely a lot of possibilities. I'm pretty sure there's some things you can do in physics that I just don't have the background to recognize. But I would like to find some people with physics background and kick around some of these ideas and see if there's some way to, like I say, encode the phase of light, for example. I'm pretty sure that's similar to what's done in holography. Find some way to do that and to read it back and to scan it.
Or just a tank of water, you can get a standing wave going. You can even do two standing waves across each other.
Yeah, definitely.
But I'm actually more interested in the first generation, and I wonder what you do about sort of power requirements and like heat dissipation, and also just kind of especially like thinking in a three-dimensional case, like if you have a clock, then how do you get everything to synchronize?
Right. And we talked a little bit about some of this beforehand. A big idea of the cell matrix is I mean, the idea is very bio-inspired, obviously. And a big part of the idea is you don't have to go for the fastest cells possible. You don't have to go to a 3 gigahertz processor in each of these. You can clock this thing very slowly and get your speed because of the parallelism. And sort of the classic example is the brain. It runs at like 100 hertz. And I mean, you don't have that many steps in the 10th of a second it takes you to recognize someone across the room. You got 10 steps. Obviously, there's a lot of parallelism happening there, and it's successful.
Where does this 10 hertz come from?
The 100 hertz?
100 hertz? Where does it come from?
I
What
have
does
a
this number mean?
It's the time that it takes a neuron to pass information from one to another.
I see.
Firing time.
And that's the fundamental timing of the brain?
I don't know.
Well, I don't think so.
No?
No, I don't think so.
What do you think it is?
It's all in the synapses. And it all happens in nanoseconds.
In
The functioning of the
themselves.
brain, you can't explain the functioning of the brain on the basis of the number of neurons that are in the brain.
Mm-hmm.
And people have tried to do that over and over and over again. It fails every time. There's something chemical that goes on in the synapses, of which there are many, many, many synapses, okay, which gives you a very much larger number of things happening at a very much higher frequency.
So it's actually something in the nature of that synaptic
I
transmission?
believe that to be the case. But
Cool.
the problem is you can't explain the behavior on the basis of the number of neurons.
Right. Okay. Well, that
So,
certainly explains why we're unable
and
to
when
do
you
that.
when you start talking about that, it's a total mystery. People don't know.
Okay.
And so using that as evidence for something, okay, leaves me a little cold.
Okay. I guess for me it's suggestive evidence.
Well, it's
certainly
suggestive evidence that there are systems which do incredible things.
Definitely. But it also suggests to me that whatever it is that's going on and where it's happening, there seems to be a lot of parallelism involved in the final outcome. I don't know if that's...
The evidence we have is that there's lots of parts.
Yeah.
And something's happening. The rest is conjecture.
Okay, I'll buy that. On your questions, well, in some of the examples that we've done, you can certainly see that even if you have a low clock rate, you can get a lot of speed out of the final system if you set up the parallelism correctly. And not all problems are amenable to a parallelism like that, but many of them are. And so you can clock this thing slower and you can keep your heat somewhat lower by dropping your clock rate way down. As far as clocking and clock skew and so on, if you were going to feed a voltage level as a clock through 10 to the 24th transistors, that's going to have a lot of problems. You're going to have a lot of thermal, electromagnetic noise. You're going to have skew and all that kind of stuff. What if you used an optical clocking system? What if you had these things sitting in some sort of free-floating fluid and you used a laser pulse and you use that to distribute your clock? Now your clock skew is probably a lot less, and you've probably got other problems that you introduce in doing that. But there may be a lot of other solutions to doing things like clocking than
not
than
use
just,
a clock.
Yeah, there's asynchronous versions of this where the clocks are all generated locally, and they specifically take care of the skew, because if it takes you a while to get a signal from here to here, it also takes a while for the clock initiation pulse to reach, and it ends up keeping things in sync, even though there's a delay there.
So the first generation hardware prototypes, they're no longer available for sale, I guess.
They're sitting in storage somewhere.
Yeah. So just what's, because I've seen the simulation software on your website, and it's really cool, and I've seen lots of these like software simulations, and they're always, like, the question that I always have is, like, how much can you actually do in hardware with the hardware that you have?
Right.
So how many cells, actual hardware cells do you have at your disposal?
Not a lot.
Yeah.
And that's a big problem because the software is slow.
Right.
The hardware will be faster. So those little Mod 88 boards, like I say, those were 8x8. That was a Vertex 200, a Spartan XCS 200, so 200,000 gates. You could fit 72 cells on that, actually. Now today, if you got the biggest FPGAs out there, like a Vertex 7, you could probably fit, easily thousands of cell matrix cells on it. And so you're starting to get to a realm where you can do some interesting work. And of course, you can put those together, and if you can drive the signals correctly, you can start making arrays of those. And for a while, we talked to Daniel Mond briefly about trying to use the bio wall to implement a cell matrix array.
So if I remember right, one of the biggest drawbacks was that besides that you have to build wires as well, you don't really have a flip-flop in make a cell, right? So you have to use 2 cells to actually build some.
You use 2 cells. It's asymptotically 1 cell per bit.
1 cell per
You use
bit.
like 11 cells to make 10 flip-flops.
Right, so that's a lot of I shouldn't say waste a lot of cells for building very simple things.
Mm-hmm.
So have you ever thought about what if I would make the cell bigger and more complicated?
Yeah.
What's the trade-off there?
There's an idea, it's called gifting. Basically, you add 129th bit to your truth table, and if that bit's asserted, then different things are happening inside the cell. For example, certain inputs are connected to a flip-flop or a multiplier or things like that. And you can extend the design of the basic cell while still preserving the sort of ability to read out truth tables and pass them around. And you can start adding in flip-flops. The mindset I kind of come from is treat these things like atoms, right? Don't worry about how many atoms you're using when you have a brick, right? Just use the bricks and build your house. So ideally you're in a realm where these things are so cheap that you don't care that you're using. And in some of the work that we've done, we sort of envision building like a smart transistor out of maybe 100,000 cell matrix cells. Creating a transistor that's able to do basic switching, but is also able to manage defects, able to find other transistors, able to identify itself and respond to pings and isolate defective regions and so on. You sort of build this smart switch, and then you start doing your engineering with those kinds of transistors. Now you've just jumped up 6 orders of magnitude in your hardware requirement. But if there's a way to manufacture these things cheaply, particularly if you can self-assemble them, or you can grow them out of a crystal from a solution or something like that, you can start getting to a realm where you design these more beefy basic switches and build up from there.
Is there a well, you said, or you showed that you can kind of go around defective parts in the array. Is there a threshold in which if you have more defective cells that you can't do anything out of?
Definitely.
Is there? Okay. So I guess then the next question is how the way you program these things. How does that depend on this regularity of interconnections between them? All of these things are in a linear array, and then 2D array maybe.
Right.
Do you have to build them like that?
Not necessarily.
Not necessarily.
Yeah.
They could be in any order. You can
Sure.
start. So your edge cell could maybe connect to something else in the middle of that array, right? Okay.
Well, it has to build a pathway there, or you have to have a pre-existing pathway
okay.
there. Yeah.
Either way, okay.
Yeah. And the examples that I showed you were just sort of one of many ways to do it. Another way to seed an area is to put an initial seed in the upper left corner and have it replicate in 2 directions simultaneously, and then have each of those replicate in 2 directions, and you sort of get this growing wave that moves from one corner down to the other. And instead of doing all of your first direction in one step and then coming down, you're sort of doing this simultaneously, growing in both directions. So it's an n squared over 2 growth instead of n squared. But it's the same idea, but there's reasons why you'd want to do one or the other, or something completely different.
More questions?
No, but I'm just thinking, it's a pity that it's still a huge leap between the Aboriginals and your story.
Mm-hmm.
Because, I mean, that's a beautiful analogy that you present there. But other than that, I don't see the connection. Other than wouldn't it be great if there were, if somehow you could capture the world in a more direct representation.
Right. Yeah, I don't necessarily see the connection either, but it's a hunch, I guess, to pursue.
Yeah, to have an image.
Yeah.
What is the genome for I don't know, like the ALU that you showed or something? Like, can you actually sort of unfold like if you start with a single cell as a seed, and you have some sort of initial configuration input, like I'm trying to understand sort of the mechanism of getting all the information that it takes to make an ALU sort of to propagate out from like a very simple unit.
The one work that we actually did that went that far was this 2002 work that you can find on the website. We basically came up with an artificial genome pattern that you had row column information, and it wasn't necessarily something that would match row column in the final array because you didn't know where things would end up because of defects. But you had these IDs for each of the pieces of your final circuit, and you basically had three parts. You told it what the function was, you told it where the inputs got connected to, and two parts. Okay, you don't need to tell it where the output gets connected to because the things that it feeds will find it. Oh, third part was for edges, if you want input or output from the outside world. And you just pack these all into a series of truth tables. So you use the truth tables as actual memory, 128-bit storage. And you don't interpret those as mapping inputs to outputs. It's just a memory function now. And so you take your circuit and you basically compile it by hand or a piece of software, and you come up with a net list. And you say node 2 has two inputs, they're connected to this, and its function is this. And that gets codified into a series of binary representations packed into this genomic string. And you put that inside this thing that we call the super cell, 73,000 cells. Genome goes down here, and you put it into the system, and it starts replicating and so on. So it's a very straightforward engineering process in some way to design what that string should be like.
What about self-regulation? I mean, an ALU is good because like once you've configured it, it does its task, and you give it inputs, you get some outputs, but you don't have to change the structure of the circuit itself. Do you have any examples of sort of dynamically self-reconfiguring?
No, only one that's really old, which was an expanding counter. It was like an overflow-proof counter. So it had a series of toggle flip-flops, and it would start clocking and building, and when it got to where the topmost bits were both 1, so it was 3/4 of the way to an overflow, it would kick off another piece of circuit, and it would add another stage to the end of it, and it would build it before it needed it. And so that's an old example, but it's the only thing I've actually done with dynamically changing circuits like that. It would be a fun area to work in, though, I think.
All right. Thanks a lot.
Yeah.
Oh, yeah.